So we're just reviewing what we were doing last Thursday. And so we have find the formula for the inverse function, make a table of values. Reversing the table of values gives us the table for the inverse function. Plotting the function and the inverse together in the xy plane, we see the symmetry across the line y equals x. So notice that if f of x is a linear function with a positive slope, so is f inverse. They both are linear with positive slope. So how are the slopes related? Well, the slope of the inverse function is actually the reciprocal of the slope of the function. Here, it's a little confusing because this superscript notation can mean exponent. Here, it does not mean exponent. It means reverse the process of the function. So not multiplicative reciprocal, but inverse, right? This is the same notation for multiplicative reciprocal or just, reciprocal. Sorry, multiplicative inverse is the reciprocal, but that's not what this denotes, right? This denotes the process of reversing input and output. Yeah, what's the formula for that would be? And we have this inverse function property that says if you take a composition of a function with its inverse, you get just the function back, right? And we saw that with our linear function, it worked, and either way, right? Both f of f inverse and f inverse of f both lead to x, right? As the because you undid what the function did, so you got back to where you started, which was at x. So here's a nice example of a function which is its own inverse, 1 over x, and you can see that it's got natural symmetry across the line y equals x. So when you reflect it, you just get the same curve. And in fact, here's a composition. So this shows the inverse function property. Moving on, we have, with a rational function, the algebra is a little bit more difficult. And also with a rational function like this, where the degree of the numerator is equal to or greater than, in this case, equal to the degree of the denominator, they're both first degree polynomials or linear functions. You can do long division and get a quotient and remainder and rewrite the function. So these two formulas are equivalent, right? And we talked about how we can perform a sequence of transformations on this 1 over x function to get this more complicated rational function by what? We shifted 3 to the left. We stretched vertically by a factor of 5. That gave us 5 over x plus 3. And then we shifted, I didn't label this one, did I? Or describe it in words. That means this is shift 1 down, right? Which is obtained by replacing y by y plus 1. And then after you solve for y, you get our nice function, right? -1 plus 5 over x plus 3. And I think we did that in GeoGebra. We showed all the process with the graphs, and that it is a 1-to-1 function. None of those transformations lose the 1-to-1ness, right? Stretching or shifting doesn't lose 1-to-1ness. So here's another example. Oh, looks like the same example. Oh, right. So finding, finding the inverse function for that function. And it has, the original function had a horizontal asymptote at -1 and a vertical asymptote at y equals -1 and a vertical asymptote at x equals -3. This one has a vertical asymptote at x equals -1 and a horizontal asymptote at y equals -3. So as you might expect, everything is reversed, right? And again, I think we did the graphing in GeoGebra, so we don't see that here. So here's a function where if you restrict the domain, you get a 1-to-1 function. Normally, this parabola would not be 1-to-1, but restricting the domain gives us a 1-to-1 function. And to find the inverse function, you need this process of completing the square, right? So we start out with this. You see that this is equal to the square of x plus a half minus a quarter, right? So when you square this binomial, indeed, you get x squared, right? You get twice 1/2 x is just 1 times x. That's that term. And then you're going to get the square of a quarter, but we're subtracting a quarter, so that cancels out, right? So this vertex form is equivalent to this descending powers form. And we can solve the vertex form for x in terms of y. We take the positive square root because we have restricted the domain to x greater than -1/2. And in that case, the inverse function is given by this -1/2 plus the positive square root of a quarter more than x. All right, well, you may recall that. I'm not going to go through the graph of all that again, but let's get into the exercises then, shall we? If there are questions, you can pose them in the chat, but I don't know, did we do exercises from the book? I think were those from the book? They didn't seem to be numbered. So let's go to the book. Who wrote the book? Oh, this is something else. Huh? Here's the book. Oh, I need to find it. Sorry. I'm here. And boom, there we go. Do we want to see the table of contents over here? Not so much, huh? So I can get rid of that. And then, can I get rid of it over here? I don't want to see all this crap on the right. I'm in Adobe reading a PDF. And can we say view page navigation? Oh, can I go back? I didn't want to, oh crap. Ah, I was just trying to get rid of, oh, I see, I can do it like that, huh? Does that work over here? Yeah, it does, okay. So now I'm gonna get back to this and maybe show me my index. Is it here? Yeah, so one-to-one functions, okay. Then I can just click on this little arrow and zoom in, all right. And I want to go to the exercises, and these are the exercises for the, oh, I think that's the review. Yeah, we can look at that, but first let's look at some of these, right? And I'm watching the chat, so you can either, you know, yell out or how come? Oh. So there, you know, the exercises start with some concept problems, fill in the blank. A function f is 1-to-1 if different inputs produce different outputs. You can tell from the graph that a function is 1-to-1 by using the horizontal line test. For a function to have an inverse, it must be 1-to-1. Which one of the functions has an inverse? Well, not the square, unless you restrict the domain, right? So it's this odd degree polynomials. Do odd functions necessarily have an inverse? Well, let's answer that question. Sorry, here. So I'm posing the question. Okay, we see f of x equals x cubed is 1-to-1, and so invertible. What's the inverse function? Well, f inverse of x is the cube root, right? So, you can check that quickly because f of f inverse is going to be f of the cube root of x, which is the cube root of x cubed, and that's equal to x, right? By definition, right? The cube root of x is the number whose cube is x. You can also, use the exponential notation. So there's another way of looking at this as x to the 1/3, right? The cube root can be represented as a rational exponent by x to the 1/3. Is that well known? Okay, well, it is now. So then the property of exponent says power to the power, you multiply the powers. So this is x to the 3/3, I guess you could say, or simply x to the 1, which is x, right? What does a table of values look like? Well, we can go -8, -1, -1/8, 0, 1/8, 1/8. Oh, sorry. So what's the cube root? What's the number whose cube is -8? Well, -2, right? Oh, sorry, I have this backwards, don't I? So let's go ahead and tabulate we're tabulating the inverse, yeah. And at the same time, we could tabulate the function, right? Because it's just a reverse. So -2 cubed is -8. So the cube root of -8 is -2, right? The cube root of -1 is -1 because -1 cubed is -1. Cube root of -1/8 is -1/2. And that's because -1/2 cubed is -1/8. Cube root of 0 is 0. Cube root of 1/8 is 1/2 because 1/2 cubed is 1/8. And there's a lot of symmetry going on here, right? When we make a graph, have we graphed this one? I think we have, but it bears repeating. I'm not averse to repeating this graph. So we want to capture outputs between -2 and 2, or -8 and 8, huh? Okay. So I'll take it. Okay, so if this is 8 on the x-axis, and half of 8 is 4, and here's equally spaced, perfectly evenly spaced hash marks going up and down, same scale on each axis, right? So this is -8, this is +8, -8, -4, 4. So here's 2 and 2, -2, -2, and here's 1, right? And those are kind of important points. So -8, -2 is this point here. -1, -1 is this point here. Here's 0, 1, 1, and this is 2 here, right? So here's 2, 8. And so the function, yeah, it comes in like this. It's going directly up near the origin. That's kind of hard to see, huh? So the inverse function is going to make this even messier unless I maybe put it in pencil, right? So -2, -8, that's if sorry, this is the function, right? So this is the inverse function. I plotted that first, right? And here's the function. It goes through these points as well, right? So they intersect there, but kind of goes like that, right? So that's hard to see. Do you see the symmetry through the line? Let's go ahead and do it in GeoGebra because it'll be a lot cleaner, huh? So I've got some GeoGebra stuff happening here, which we can erase. And this is gone, and that's gone, and that's gone. And we want x cubed. Yeah, see how flat it is where it passes the origin? And here is x sorry, x to the 1/3 power, which is also the cube root, right? And here's the line y equals x, yeah, which is the line of symmetry, right? That's not one of the functions. So let's change its style to be dashed, and it's green. If we have a different scale going on here, right? So yeah. So now it's pretty much the same scale, is that right? Maybe more like that. So yeah, you can kind of see the symmetry. And I didn't capture 8. Well, there, right? So you can see 2, 8 is a point on this curve, and 8, 2 is a point on the other curve. And we could plot those. But yeah, so this I'm finally getting around to the question I was going to ask earlier, which is this is an odd function, right? It's an odd polynomial function, and it's invertible. We got an extra parenthesis here, and we see, you know, here's the symmetry. I'm going to draw this line segment connecting these, and you can see that it's perpendicular to the line of symmetry, right? Yeah. And this point 1, 1 and 0, 0 and -1, -1 are on both curves, and so that's where they intersect the line of symmetry, right? So the follow-up question here is, can we generalize this? So, you know, how about f of x equals x cubed plus x? That's also an odd function. How do we know? Well, the powers are odd, right? So f of -x is the negation of f of x, right? That's the definition of an odd function, right? And because what? Well, when you cube a negative, you get a negative. And the negative of x is -x. So yeah, I mean, it just works out, right? Watching the chat, okay. So is this also 1-to-1? Well, let's see. It's hard to tell, right? Is this 1-to-1? How do you tell? Well, you look at f of x1. If that's equal to f of x2, does that mean that x1 equals x2, right? Well, here's the formula, right? Does that mean that if the cube of one number is equal to the cube of another number, does that mean the two numbers are equal? Oh, sorry, I forgot, I didn't write the whole function, did I? So this is x1 plus that, and then this is x2 cubed plus x2, right? Ah, okay, so this is a little tougher, right? So what I'm going to do is use the subtraction property of equality. I'm going to subtract x2 from both sides, and I'm going to subtract x1 cubed from both sides, okay? All right, do the same thing to both sides. You get an equivalent equation. Or subtract the same thing from both sides, you get it. So, yeah, so this is going to be x1 minus x2 equals x2 cubed minus x1 cubed. Did we learn how to factor a difference of cubes in intermediate algebra? Yes, we did. Well, we weren't together, but I've taught that class often enough to know. Where's my mug can? The mug can is missing. I've taught that class often enough to know that, yes, you have learned how to factor a difference of cubes. And so I'm going to rewrite this equation over here, okay? So it's on the left side, we have x1 minus x2, I guess to the first power, but that, yeah, I don't know why I wrote the power in there. It's not needed, is it? So that says that x2 minus x1. Oh, there isn't space. I'm going to go to a new sheet of paper. Okay. So let me remind you what we had. We had f of x1 equals f of x2. We'll do this from scratch because it was a little messed up, right? So this is x1 cubed plus x1 equals x2 cubed plus x2. And we're trying to see, does that mean that x1 equals x2? And it's not obvious, right? So I'm going to do what I did before, which was subtract x2 from both sides and subtract x1 cubed from both sides, right? And then I'm going to factor this difference of cubes. So x1 minus x2 is still by itself over here. Over here, and tell me if this doesn't look familiar. It may not, because it's, you know, it's one of those topics maybe you spent a few days on, it was on the exam maybe, and then you forgot about it. Well, maybe it was on the final, right? Difference of cubes. So does it work? Shall we check it? Sometimes I use the finger method of multiplying. This has got, each one of these has got, each one of these two has got to multiply each one of these three by the distributive property, right? So that gives us 6 products. We only see 2 up here. And what are they? Well, they're x2 cubed, which you get from x2 times x2 squared, right? And negative x1 cubed is from negative x1 times x1 squared, right? So this product and this product we see on the top, but we don't see the other 4 products because they're in pairs of canceling terms, right? So x2 times x2 x1 is x2 squared x1, and this is negative x2 squared x1. Here is x2 x1 squared, and here's negative x1 squared x2. Those are opposites, and so they cancel out, right? Now I'm going to say that on the left side, I've got the negation of x2 minus x1. And I'm just going to copy the rest of this over, right? All righty. So if x1 is not equal to x2, certainly if x1 equals x2, then this statement is true. So this is true if x1 equals x2, which is what we're trying to show. So what we're going to do is assume x1 is not equal to x2 and see that that leads to a contradiction, okay? That will be sort of a proof by contradiction that in fact f of x1 equals f of x2 if and only if x1 equals x2. All right, so if they're not equal, then I can divide both sides by this difference because it's not 0, right? You can divide by a non-zero quantity. So then that's going to be, we can then conclude that this is equivalent to saying -1 equals x2 plus x2 x2 squared, right? Plus x1 squared. Okay, what kind of thing is that? Well, it's quadratic, right? Do we know how to solve quadratics? Yeah, complete the square, right? All right. So I'm going to rewrite this with 0 on one side. Just add 1 to both sides and reverse the sides, okay? So x2 squared plus x1, x2. I'm kind of reversing these factors because I want to think of this as quadratic in x2, okay? So you could plug into the quadratic formula. So this is quadratic in x2 with coefficients. What would the coefficients be? Well, a is 1, right? That's the coefficient of the leading term. B is the coefficient of x2, that's x1. And C is x1 squared plus 1. Now, do you remember the quadratic formula? I'm not going to do this by completing the square. I'm going to get cheesy and use the formula. In fact, I'm not going to use the whole formula. So x2, the value of x2 that will make this equation true is, here's the general formula. You recall this, b squared minus 4ac all over 2a is real if and only if b squared minus 4ac is not negative, right? So it's greater than or equal to 0. Okay, well, that means that x1 squared minus 4 times 1 times x1 squared plus 1 has got to be greater than or equal to 0, right? Okay. And these are like terms. So we got 1 minus 4 is negative 3x1 squared minus 4. That has to be greater than 0, but that's a contradiction, right? Because this is a negative. We're subtracting 4 from a negative. That can't be a positive number, right? Therefore, this is the symbol for therefore. F is 1 to 1. Okay, so we've seen two examples of, here they are. We saw x cubed, that's an odd function. X cubed plus x is an odd function. So you might generalize at this stage and say, look, all odd functions are 1 to 1. And I would disprove that with a counterexample. So let me say, however, and then we'll get to the exercises, okay? Not all odd functions are 1 to 1. It's 1 to 1 is the way that's written out in words, right? And here's a counterexample. An example of an odd function which is not 1 to 1. F of x equals x cubed minus x. I contend that that's not 1 to 1. And here's the evidence, right? F of negative 1 equals f of 0 equals f of 1. They're all 0, right? Which you could see more clearly if we were to factor this, right? F of x equals x cubed minus x. You can factor out an x, right? And then you've got a difference of squares, which you can factor. So that's x times x minus 1 times x plus 1, right? You can see that that's 0 at x, it's 0 at 1, and it's 0 at negative 1. If any one of those three values will make one of these three factors equal to 0, and then it does not factor. Okay, so we have three different inputs that produce the same output. And what does the graph look like? Well, it looks kind of like this. So here's 1, here's negative 1, and you can see that doesn't pass the horizontal line test. You can see that does have origin symmetry though, right? If I were to draw a line segment through the origin from a point over here to a point over there, you would see this point is reflected through the origin to that point, right? So hard to see. Yeah. So it's got origin symmetry. It's an odd function, but it's not 1 to 1. All right, so let's get to the exercises, for goodness sakes. Oh, those are not the exercises. These are the exercises. Okay. And we had, oh, what happened there? We went back to the beginning. Oh, well, that was unfortunate. I don't know. I didn't ask for that, as far as I know. So I want to go here, and I want to get rid of this, and then I want to zoom in. Oh, and then I want to go down to 1 to 1. exercises. Are the following one-to-one? Well, even functions are not one-to-one unless you restrict the domain. So is this one-to-one on this little piece here? And yeah, right, because the line of symmetry for this is going to be the y-axis. And so is that obvious? X to the fourth plus 5, it's x to the fourth shifted up 5 units, and x to the fourth has y-axis symmetry. So if you just include this little segment where x is positive, that piece of it will be one-to-one. Reciprocal of x squared, well, no, that's an even function. So if you don't restrict the domain, it's understood that you're using the largest possible natural domain, and it's not one-to-one there. 1 over x, that's a classic one, right? It's its own inverse. So we studied that earlier. I don't know why does it do this? I'm not asking for that. It's misbehaving. I have to do this again. Go there and stay there. All right. So these are one-to-one. So to find the inverse, what do? Well, we had a bunch of problems like this, didn't we? Or maybe not in the exercises. How are we doing on the exercises? Maybe we should, the homework assignment. There were a bunch of these, right? So basically, you want to find the symmetric point, right? Through the line y equals x. And, these are not labeled very well, but, this is the point 1, -1 here.
Oh, Professor, I'm sorry. Are you recording?
I thought I was.
Oh, yeah, no, it says it. Never mind. My bad.
Yeah, no worries. So yeah, if we zoom in on this, we can see this a little more clearly. You're going to have a symmetric point over here, right? So you just plot. So this is on the line, or is it? What are the coordinates here? This is -1, -2, so it's not on the line, right? So the line of symmetry is the line going through the origin here. Let's do this in GeoGebra. So I'm going to transfer this over to GeoGebra, which is here. Okay, and we can get rid of this stuff. And I'm going to plot this function just by drawing these segments, okay? So I have a segment from, let's zoom in a little bit here. Should we turn on the grid lines? Options, advanced. Is it this one? The grid. Show grid. Yeah. Just the major grid lines will do. Okay. So now we're looking at the grid. So we can say, yeah, we got a line segment from -1, -2 to 1, -1, right? And then from 1, -1 to 2, 2. So that's on the line of symmetry, huh? And then, it's just going to follow the line of symmetry from there, right? Okay, so what does the inverse function look like? Well, let's graph the line y equals x. So there's your line of symmetry, right? And I can make that dotted. I don't know why I insist on it being dotted, but I do. Dashed, dotted, whatever. So the symmetry here is going to take you to this point, and then that point, and then from that point to this point, and then the rest of it is on the line of symmetry, so it doesn't move, right? Yeah. So that's the that's the idea of that thing. Where? Oh, I didn't mean to do that. I guess I want to do this. Okay. And that, okay. Let's see if I can scroll down here without going. Finding inverse functions, restricting the domain, applications, fee for service, Torricelli's law, blood flow, income tax, multiple discounts. I don't know, any preferences here? No dogs on campus. Demand functions. Well, let's just pick a few of these, okay? Torricelli's law. So a tank of 100 gallons of water drains from a leak at the bottom, causing the tank to empty in 40 minutes. According to Torricelli's law, the volume of water remaining in the tank after T minutes is given by this function. So it's f of t so this is 2.8, number 95. And the V is the volume of water in the tank. And T is time in minutes. We didn't say what the volume is measured in, right? Do they tell us? Gallons. Okay. So V equals F of T equals 100 times 1 minus T over 40 squared. So how was Torricelli's law developed, do you suppose? Well, that's a good question. So it takes 40 minutes. So this is a quadratic, right? And you can see at T equals 0, you're going to have your 100 gallons, right? 1 minus 0 squared is 1. 100 times 1 is 100. At 40, you're going to have 0, right? So it meets those two restrictions, that it's full at time 0, and at time 40, you're going to have 1 minus 1 is 0, right? Squared is 0 times 100 is still 0. So what is the shape of the curve in between? Well, it's a downward opening parabola. No, it's upward opening parabola. Wait, that can't be right. Then the volume would be increasing. Oh, the vertex is at T equals 40, right? Is that obvious? Yeah, I say it's obvious. It's kind of in vertex form. Is it in vertex form? How would we write this in vertex? What's vertex form? Vertex form is A times T minus H squared plus K, where H and K are the coordinates of the vertex, right? So we got this 1/40th sitting there. So I would contend that we can factor out the square of 1/40th. So we could say this is 40 minus T all over 40, getting a common denominator. And then 40 squared is 1600 times 100 is going to be equal to 1600 times 100. That's 160,000 times 1/40th minus T, quantity squared. And oh, that makes it look like the vertex is at 1/40th. I think I did that wrong, right? Sorry. Yeah, this is 40. I did do that wrong. What was I thinking? I don't know. It's 40 minus t, right? So let me rewrite this once here. If I confuse myself, I'm no doubt confusing others. So 40 minus t all over 40, right? That's equal to 1 minus t over 40. So then, oh, yeah. So, oh crap. Let's get a new sheet of paper. Professor can't do algebra. All right, so let's start afresh here, right? I just want to get vertex form out of this, just to show you that it's possible, right? Okay, so let's take it baby step by baby step, then I'm less likely to make a big fat boo-boo. So we get a common denominator, right? Then I pull out not 40 squared, but 1 over 40 squared, right? Which is going to be 1 over 16, or we'll have 100 over 1600, which I think we can just write as 1 over 16. 40 squared is 1600. So 100 divided by 1600 reduces to 1 over 16. And now this is 40 minus t, right? But we can also write this, since that's a square, it doesn't matter which way you form the difference. The square is going to be still the same, right? You'll still have a t squared, a minus 80t, and a plus 1600, right? So now when t equals 0, this is going to be 1600 divided by 16 is 100. So we get what we wanted, right? That 100. And when t equals 40, it's going to be 0, right? 40 minus 40 is 0. 0 squared is 0 times what 16th is still 0. Okay. So this is vertex form. We can see that the vertex is at 40, 0, right? When x is 40, you could write a plus 0 here if you wanted to see k is 0. And so when we graph this thing, we're going to see, okay, here's 40, here's 100. This is the t-axis. This is the v-axis. We're plotting volume against time, and it's a parabola. So I haven't plotted a lot of points. I just know that it's a vertex, the parabola with a vertex at 40, 0, and y-intercept 100, right? Or v-intercept, if you like. Okay, and this is 1-to-1, is it not? Yeah, this part of the curve is 1-to-1. So this function only applies on the interval. So the domain here, and this is because of physics, right? Not because of the math, but because of the physics. Domain equals the interval from t is 0 up to 40 inclusive, right? And on that restricted domain, this is invertible. And what's their question? Find the inverse function. Oh, find the inverse, and what does it represent? Okay, so part A is find, so we called the function f of t, right? V equals f of t. So find f inverse. And what does it represent? Notice they don't say f inverse of t, because it wouldn't make sense, right? Because t is time. And so to rename the variables here doesn't really make sense, right? Because they're not abstract, they're concrete. T is time, V is volume. It would be funny if V were time and T were volume, right? So the formula for the inverse is going to be a function of V, right? We're not going to rename the variables. And how do we find that, right? Well, we want to solve for t in the equation v equals, and do we care which form of the equation we use? Not really. Let's use the second one. 1 over 16 t minus 40 squared. Can we solve that for t? Yeah, start by multiplying both sides by 16. then we're going to extract roots. So we're going to extract the negative root or the positive root? Well, the positive root, right? Or is it the negative root? That's a good question. Well, let's put the positive root. We can add the negative if it makes sense. So I'm going to start out with the positive root. But the next step would be to add 40 to both sides, right? Ah, yeah, I need the negative root, right? So t is going to be equal to 40, take away the square root of 16v. So if v equals 0, yeah, we're at 40. If v equals 100, then we got the square root of 1600 is 40. We have 40 minus 40 is 0. And that's correct. When the volume is 100, we're at times 0, right? So that's why it makes sense here to take the negative square root. And so this is 40 minus 4 times the square root of v. I've taken the square root of 16 out, right? Okay, and in this case, it really doesn't make sense to rename the variables because they have meaning, and you can't change the meaning in a sensible way here. And you also, probably, so can we plot the inverse function here and see the symmetry? Well, first of all, we're obviously using a different scale on the the horizontal and vertical axes. So that would skew the apparent symmetry through the line t equals v. But yeah, what you could, what would the inverse function look like? So you'd swap intercepts, right? But this is also the inverse function, right? This is t as a function of v. Just turn the paper sideways and maybe upside down, right? Then you can see this is t as a function of v. It bleeds right through, so that's great. So you can get a curve for the inverse that way. What would it look like? So this is like 40 and 100 out here somewhere. So you would see a curve. If you were to actually swap the variables, you would see a curve like that. And the line of symmetry looks like this. But that really isn't needed here. All righty. More questions about that or more applications? Blood flow. Got blood moving through a vein or an artery. It's a boundary value problem because at the edges of the vein or artery, what am I doing here? I can't see the horizontal scroll bar for some reason. Yeah, Adobe not so great sometimes. It's a lot of money. But I see the vertical scroll bar, but I shouldn't have done that. Oh, deep into chapter 3 now. It's very sensitive. Oh. I think we're in here, right? Oh, these are more, this could be the review section. Yeah. So let's scroll up here. Maybe page up. Is that faster? So this is in the review. Okay. Here's the blood flow problem. Oh, and now I do see a horizontal scroll bar. Okay, it's not fitting in the page because I don't know why. Oh, I see. So I want this one. There we go. Blood flow. As blood moves through a vein or artery, its velocity v is greatest along the central axis and decreases as the distance from the central axis increases. So the central axis is this dotted line, right? You see the radius, it's a cylinder, right? And the cross sections are circles then, right? And the radius of a cross-sectional circle is indicated here as r. And the velocity of the blood depends on how close to the boundary. At the boundary, the velocity is 0. As you get more towards the center of the tube, the velocity increases. It sort of is indicated by these arrows. And there's a function given for that. And they want us to find the inverse. All right, let's try it again. Maybe we can do this one, number 96. How are we doing? It's getting on the 13th hour. So this is number 2.8, number 96. And here we've got the velocity of blood, and this is in centimeters per second. And r is the distance from, what are they calling it? The axis, central axis. I'm abbreviating central, okay? Central axis. No, it's the same abbreviation for control. Central. Okay, so we get the velocity as a function of r, and they're writing the function as g, is 18,500. Wow, that's a lot of centimeters per second, times 0.25 minus r squared. Okay, so this is different from Torricelli's law, because in Torricelli's law, we have the square of the difference. Here we have a difference of squares. You see that? A quarter is the square of a half, and r squared is the square of r, right? So we could write this in factored form. So 18,500, and you'd have 1/2 minus r times 1/2 plus r. Is that? Yeah, 1/2 squared is a quarter, which is 25 hundredths, or 0.25. And then the opposite terms cancel out. And so we see that r should range between 0 and 1/2, right? Is that clear in the statement of the problem? R is the distance, right? So yeah, r should be a number between 0 and 1/2. If r is 0, then the velocity is a quarter of 18,500, or what, 4,750 centimeters per second. That's pretty fast. It's whipping along. That's some fast blood. Whereas if r is 1/2, then you're at the boundary, and this factor becomes 0, and so there's no velocity at all. The blood doesn't move at the boundary. Okay, so they want us to find the inverse function. I think for that we may want to complete the square. Do we have a complete square? We kind of do, huh? Yeah, so I guess I would expand this, right? So to find G inverse, I'm going to say G inverse of V, right? Because it doesn't make sense, again, to rename the variables. So the output variable of this function is V. That's the input variable to the inverse function. And I'm going to write it as negative 18,500 r squared minus, what do we say, 4,750. Is that 1/4? So if I multiply that by 4. I'm going to get 18,500. Is that true? Half of this is 9,000. Oh yeah, no, I think I screwed that up. Half of this is 9,250. I have to write this out. What's that divided by 2? That's 4,625. Okay. Shouldn't do things in my head. But this is in vertex form, right? So we want to solve for R, and since it's in vertex form, that'll be pretty easy, right? So this is, the output is, sorry, this is, I'm sorry, I wrote this badly. V equals this thing. We want to solve this equation, as mangled as it has become, for R in terms of V, right? So to find the formula for G inverse, write down the equation without the function notation, and I expanded the right side, right? Yeah, half of this is 9,250, half of that is 4,625. Okay, so I want to solve this for R, and I'm going to say add 4,625 to both sides. I'll have negative 18,500 R squared. Then I want to divide both sides by this thing and say R squared is negative. Oh, I'm sorry, I don't know why I have a negative there. I really have made a mess of this. My apologies. I don't know. What am I thinking? I'm not thinking. Okay, does that better? Right? See, I just distributed this 8. If you see something that's wrong, say something. Yeah. So, all right. So to find the inverse formula for the inverse function, write down the equation, dependent variable in terms of independent variable, and I did distribute this. Oh, I know what the problem is. Hang on, I'm going to get this right. Oh gosh, these things are recorded, right? Okay, so we have G of R, V equals G of R is given by the formula 18,500 quarter minus R squared. If we expand that, we get V equals, I'm going to write 4,625. That's this product. I don't know why I had a negative on that. That was my mistake. There is a negative on the other term, right? 18,500 R squared. Is that better? It's not nearly as complicated as I was making it out to be. So we want to solve for R in terms of V, right? That's the process for finding a formula for the inverse function, right? So I would add this square term to both sides and subtract V from both sides. So you have 18,500 R squared equals 4,625 minus V. Is that agreeable as an equivalent equation, just using the addition and subtraction properties of equality? And then we'll divide both sides by 18,000. So R squared is equal to, and that's just going to give us 1/4 here, right? Minus V over 18,500. Then we're going to extract roots. And which root do we want, positive or negative? Well, we said R had to be between 0 and 1/2, right? So we can write R as the positive square. It's got to be positive, right? It's a distance, right? So 1/4 minus V over 18,000. Can we simplify this? Yeah, I'm going to say let's factor out the square root of a quarter, which is a half. And then we'll have v divided by 4,625. So we see that when the velocity is 4,625, that's the maximum velocity. That means that r is 0, right? 1 minus 1 is 0, square root of 0 is 0. And we're on the axis, the central axis, right? Going as fast as we possibly can, which is about 46.25 meters per second, 100 centimeters in a meter. And that's the inverse function. So g inverse of v gives us r, and we would take the positive. So that's always a question when you're taking roots. You ask yourself, do you want the positive or the negative? And do what makes sense. Okay, so I want to, before we wrap up here, I want to do a couple of things. One is to look at the calendar. Do we have a calendar somewhere? I think it's back in week 2 or something, isn't it? Oh, week 1? Where's the calendar? Is it in the syllabus? We should have the calendar here, huh? I'll tell you what, let me add it to, so I'm going to say add file, and I should have the calendar here. I don't see it as one of these listed files. Huh. Well, let's cancel that. Let's go to the syllabus. Okay. So here we are. Oh, well, that's the calendar that's built in, right? Pretty sure we had a calendar. Okay. Let's go back to modules. I'm just going to find it and add it. So I'm going to add new, not an assignment, but a file, new file. I'm going to browse for it and find it in my browser. Well, in my directory. Listings. And we got a lot of files here, huh? Syllabus. Pretty sure we had a calendar. Five, chapter this, chapter that. Well, I will find the calendar, but for now, let's put up a chapter 2 test. That's the other thing I wanted to do. To give you an example of what's been offered in the past, and an add item. Okay, that's published. So take a look at that. Those are typical kind of chapter 2 questions I've asked in the past, I would imagine. And we can talk about these. Oh, this is a pretty short one, huh? Well, it's got multiple parts. Yeah, you only got, what, 70 minutes, right? So it says you may not use your books or notes. Well, you may use a calculator. Oh, okay. Well, great. So we have that, and I will find the calendar and post it. Any questions before we quit? We're now a couple minutes over. Chapter 2, sorry, the geometry tests. Some of you probably have yours back already, and I just, I don't know how to put them in a separate. Ordinarily, I grade them and then return them all at once, and I just don't see how to do that here. So I'm about a third of the way through. Yeah, sorry, there's somebody's going to ask a question.
Yeah, is this just a sample of our next test?
Yeah, this is not the test. This is
Okay.
just an example of what I've had in the past, right? So you can see how they will look. It says to write all your responses on separate paper, right? So in that way, you know, I'm not limiting you to a little box that you need to stay inside of, right? You can use as much paper as you like. And I encourage you to do just that. Don't crowd into a corner. And when is that going to be? Well, I don't know. We can review tomorrow and test on Wednesday, and then Thursday we could start trigonometry proper. That seems like a good plan. So let's shoot for that.
Is this like a take-home one, or are we gonna?
No, it's somebody else asked about that, and no, it is not the exam. It's so. In fact, let me say that in the so that there's no confusion about this. I'm going to say edit this, and well, let me unpublish, and then I'll add a discussion item. Not for points, just for context, right? So example of old chapter 2 test. And then I'm going to edit that. Oh, yeah, I keep forgetting. You have to open it and then edit the thing you get when you open it, which is to say, here's an example of an old chapter 2 test. This is not the exam, to be sure. It's just a way of seeing what's typical. Okay, and then I'm going to provide a link to a page. Oh, there's the calendar. Huh. Okay. I'm not sure if that's the calendar that I had in mind. It's a calendar. Files. It's chapter 2. I think that's it, huh? Okay. And then we'll save this. That makes it a little bit clearer what's going on here, right? Does that actually open it? Yeah, okay. So if we go back to modules, you can see that we can just delete this. Alrighty. Okay, I think there may be people waiting in my office, so I'll bid you adieu and a pleasant afternoon.
Thank you, Professor.
You bet. Ciao for now.